here today. Okay, so machining, again, this is, I'm sort of flipping around here a little bit because this is what we have in the lab for the most part. We don't have too much in the way of equipment beyond machining. And I'll just sort of go through this sort of quick because some of it we'll do in the lab. But machining basically is the process of taking in this case, a forging, a crankshaft here, and making basically the journals much more precise, improving the surface finish, and making the dimensions much more precise than they would be right out of a forging operation. That's typically why you do it. Forged is not dimensionally good enough to fit the need, so you need to machine it to get it with a better surface finish and a better dimensional characteristic. But you can also see that some aspects of this crankshaft may not need to be machined, like these sort of the throw on the crankshaft, where you're going from the center journal to the journal that would be driving a connecting rod. I'm not sure if those are machined at all. Probably just shot peened, just to get the surface cleaned up a little bit, but not machined, because the forging is dimensionally good enough, and the surface finish is certainly good enough because it doesn't contact anything, that you don't need to do anything beyond that. So that's pretty typical, and that's why I show this image. You don't necessarily need to machine everything, just whatever requires a good dimensional characteristic, precision in the dimension and tolerancing to do that. The other thing which you see here is that these oil holes are put into the journal as well. These little holes. I don't know how well you can see it on the screen there, but these little holes are what carries the oil through the connecting rod, ultimately to lubricate the bushings where it mates up with the connecting rod. And those are machined in. You can't forge something like that in. You need to machine it post forging. So that gets put in there as well. So almost all the machining that we do creates a chip in some way, and that's sort of a category, if you will, of chip forming processes. There are some machining processes that we don't have here that don't, although we will have some. Machining still is there's some processes that sort of fit into machining, things like water jet cutting. You could argue you're creating a chip that's just very, very small. Things like EDM processes, again, you're creating sort of dust. Is that a chip? I guess you could still sort of call it that. But in all cases, you're removing material. Okay, that's sort of the common thread. And just some of the nomenclature behind some of the processes. You've got turning processes, which are on a lathe where you've got a piece of material. The piece of material spins, and you've got a tool that contacts it and creates a chip. And that's what you're seeing here. This would be a chip that's being created. You've got this tool, and we'll talk about some of this in a little bit more detail. Things like the angle that tool is at, the rake, the clearance on the front, all impacts how that chip is created and what kind of surface finish you're going to get and what kind of speed you can get. It's all about speed. Why do I care about speed? Why do I want to do this fast? Time is money, right? The faster I can do it, the more I can make, the more efficient I can be, right? So you want to typically on machining operations, you want to go as fast as you can, but there's limits. There's physical limits to how fast you can go. And again, things like friction, right, come into play. Things like heat come into play. As I'm machining something, it typically is going to get hot. Can I keep it cool? Can I get an adequate surface finish? One of the concepts we'll talk about in both milling and turning is the concept of feed, and that's how fast I'm moving. There's two basic sort of characteristics that I look at in machining. One is speed, that I'm either spinning the workpiece in this case, or speed I'm turning the tool in this case as well. And then feed, which is how fast I'm moving the tool relative to the workpiece. In lathe operations, typically the feed is given in inches per revolution, or millimeters per revolution. So every revolution that part makes in the lathe, how much did I feed it? Okay. The bigger that number is, the coarser the surface is going to be. Okay. You think about that, right? The faster that I feed it inches per revolution or millimeters per revolution, the coarser that surface is. To the point here where it almost looks like it's been threaded. Okay. And then with the converse of that is the slower I feed it, the smoother my surface is. Okay. And same sort of thing with milling, although not quite to the same degree. Milling, typically the strength of the tool is what limits that, and vibration and other things too. But with lathes, it's sort of a direct relationship to surface finish in terms of feed rate. The other thing we look at is depth of cut. In other words, how much material, and you can see that sort of in that image, how much material am I removing per pass? Okay, so I can't, if I'm turning this thing down maybe to half of what the diameter is now, I can't do that all in one pass. I just break the tool. I'm just going to generate so much force on that tool, it's going to break. So I need to take individual passes as I do it, and sort of logical. Same thing with milling. You can see in the slab milling, which I'm showing here, you can see that the depth of cut would be from the surface that I started with to the surface that I finished with. And you can see with this type of cutter, think about for a second the structural situation here. Cutter like this versus a cutter like this. This cutter on the left, this slab milling, it's not really shown, but there would be supports on both sides of that cutter, on the shaft, on both of those journals. There'd be massive bearings that are sort of holding that cutter in place. So I've got a much stronger structural sort of setting in that I'm not going to get deflection of my tool, I'm not going to get as much vibration, versus end milling, which is what I'm showing here, where that end mill is just hanging out. It's only supported up above on the tool holder. It's got a lot of extended length there that leads to vibration and leads to bad things. Okay. So again, chip making operations, and this is with more traditional machining operations, like we have at least currently in the lab, where I've got a tool, either a lathe operation or a milling machine or a machining center, where I'm actually creating a chip. And this is some of the characteristics that we look at. This is really a science, really, because it's dependent on a bunch of different things. First off, being whatever I'm machining, whatever the material is it aluminum, or is it steel, or is it copper? Each of those has their own issues and own characteristics that become important. Typically, as a general rule, the stronger the material is, the higher its yield strength, and the higher its ultimate strength, the more difficult it is to machine. And that's sort of logical if you think about it. I've got to exceed, and when I talked about materials, I talked about the stress-strain curve, and I said that we're really interested in the area above the yield strength, from the yield strength to the ultimate strength and beyond, right? And the reason is because of this. I need to deflect this material. I need to create a chip. Basically, I need to deform the material and then have it exceed the yield strength at the interface between the tool and the workpiece, right? Because if I don't exceed the ultimate strength, what happens? I'm not creating a chip, right? Something's going to fail. Okay, either the tool's going to fail or the workpiece is going to fail, because the power of the machine is such that one of them is going to fail, and that's sort of a general rule. So I need to control a bunch of things to get that to happen. Things like the shear angle that I'm creating. Things like what's my rake on the tool, what's my angle, and that's related to what kind of shear plane I'm going to get. How much relief do I have? Okay, and I need to have some relief because I don't want to be scraping the backside of the tool on the finished surface, right? But if you think about it, what happens is I make this relief angle bigger. What happens is I make that bigger and bigger? Tool gets weaker, right? Just think about it from a structural standpoint. I've got a force that I'm imparting on that face of the tool. As I make that angle steeper and steeper, or bigger and bigger, okay, it's less likely to rub, but it's getting weaker. Okay. Same thing with the nose radius on the tool. If I have a dead sharp corner like I have here, what's going to happen? It's going to wear faster, right? more it wears, the more round it gets, the harder it is to cut, because I've got more surface finish of the tool involved in the workpiece. Okay. So an in-depth study of this is well beyond probably what we're going to do in this class, but just wanted to make you aware of this. If you get involved in a manufacturing company and you start doing machining, the whole selection of the tool is obviously dependent very much on the material that the workpiece is made out of, but it is very much of a science as well. And what we're really trying to do is get a tool that's strong enough that the workpiece will fail before the tool does. So typically you're using materials that are very, very hard, hardened steel or carbide or some sort of ceramic that far exceeds the ultimate strength of the workpiece. And the reason, we talk about, especially in machine elements in the design side of things, we talk about materials and why some materials are used more than others. With machining, the easiest thing to machine, and sort of there's a machinability index that's attached to each material that's used. And copper, ETP copper, electric tough pitch copper, which is just pure copper, is categorized as 100 on the machinability index, meaning it's effectively the easiest material to machine. You get something like an alloy, a high temperature alloy like an Inconel or Hastelloy, you may be down in the 40s or 30s or even less in terms of machinability. So when you're selecting a material to make a product, that's one of the things you want to look at. How is that product going to be made? If it's going to be made using a machining operation, you want to lean towards materials that are easy to machine, like copper, like aluminum, like low carbon steel. I talk about, again, on the design side of things, I talk about using low carbon steels. Why is that used in so many applications? And the reason is it's fairly easy to machine, it's easy to weld, there's just lots of characteristics of it that make it easy to manufacture a product, so it becomes a popular material. So if we look at the various characteristics that we have control over, and some that we sort of don't, but factors that either direct or indirectly we control. The first is the cutting speed, the depth of cut. So cutting speed being how fast I'm spinning the tool or how fast I'm spinning the part in the lathe. The depth of my cut, how much material am I removing per pass. My feed rate, how fast am I feeding the tool. And then finally cutting fluids. And cutting fluids come into play two different things. Cutting fluids do two different things with machining. And what do you suppose they might be? Cool it, right? Most times, a lot of times you'll hear the word coolant, right? Well, that's because it cools the workpiece. So it removes the heat from that interface between the tool and the workpiece. What do you suppose the other characteristic we look for in cutting fluids are? Lubrication, exactly. And so whether it's to some degree you can get both characteristics in a cutting fluid, but typically cutting fluids are either really good at being a coolant or really good at being a lubricant. And it depends on the type of cutting you're doing. If you're working in a higher speed type machining operation, either on a lathe or in a milling machine or machining center, typically heat's your biggest concern. So you've got a cutting fluid that is really good at being a coolant. If you're working in more of a high pressure type machining operation, and we'll go through some of these, like a broaching operation where it's relatively slow speed, but it's a lot of force being generated, then you typically lean towards or gear cutting operation, you typically lean more towards a cutting fluid with good lubrication properties. The other thing that we directly control are the tool angles, and we talked about that a little bit, but this image gives you a little bit better view of that as well. Couple different angles. I've got a rake angle, I've got a clearance angle that I have control over, and that has a large impact on what my workpiece or what my shear plane in my workpiece comes into. And that's important because that's how the chips are formed, is through a shearing operation. So the tool angle, again, that's something I have direct control over. The other things I have control over certainly are the tool material. Am I going to use a high-speed steel? Am I going to use carbide? Am I going to use a ceramic? And again, it's somewhat beyond this course in terms of all that selection property or process, but just be aware that there's lots of different tools out there. They each have different characteristics in terms of wear, how fast they wear, how sharp of a corner you can get on the actual cutting edge, how impact resistant they are, how well they deal with high temperature. So all those characteristics come into tooling. And it's actually sort of a subset of manufacturing engineering called tool engineering, where that's what you do is design tools, because it is a very involved kind of thing. It's not a simple, process. So some of the things that you look at, okay, sort of that you have indirect control over, are what my chip looks like. Is it a continuous chip? Think about when you're drilling a hole. I don't know if you drill a hole in a piece of metal, but you typically get sort of curly kind of chips coming off, right? They sort of curl off of the drill. That would be a continuous chip. Advantages and disadvantages of that. Typically, your surface finish will be better because you don't have that discontinuous fracture of the chip. It sort of peels off nicely. But think about if you're doing that on a lathe. Think about a lathe operation, right? If you go back here to our image of a lathe. Think about if I had that kind of chip coming off of that lathe. So instead of this chip coming off and fracturing and being something that I can sort of handle easily, it's coming off in a big, sort of curl like that. How am I going to manage that, right? I can't have these massive chips coming off. What happens to a chip when that happens?
Hot, it's sharp.
Right, it's nasty. You're standing by the lathe. It's not a good place to be. What else happens to it? Wraps itself around the chuck. Wraps itself around the workpiece. Looks like a bird's nest. I mean, it's a nasty thing. Gets a good surface finish, but it's pretty difficult and dangerous to manage.
Flying razor blades.
Yeah, it's like standing there with spinning razor blades. So, some advantage in terms of the surface finish you get, but very difficult to manage. Okay, so built-up edge chip, meaning, so that's where the material is deforming and it's getting so hot it's actually melting a little bit and it sticks itself to the tool. That's the worst one you can get. You got poor surface finish. You break the tool sometimes doing that. Very bad. That's another characteristic you would not want to necessarily have. Discontinuous chip, that's typically what you're looking for, and that's what we're showing. That's what I'm showing here, where the chip is fracturing. Okay, it is dislodged from the workpiece on the shear plane, and then it fractures, and it doesn't come off as a continuous chip. And that's easier to manage, and that's what we typically want. If you looked at, if you remember from lab, we did that machining on the plastic, and with end mills you always get a discontinuous chip because you've got multiple cutting edges, but that would be an example of a discontinuous chip. Separate, easy to manage, not dangerous, not wrapping around things. But with drilling operations and lathe operations, where that single cutting edge is engaged in the workpiece as it's being cut, you can wind up with continuous chips pretty easily. Okay, what else do we look at? Temperature rise. Temperature in machining is never an advantageous thing to have. So you're always looking to reduce that temperature, and it's going to be reduced with some sort of coolant, or it could be even an air, a jet of air that you're shooting at the tool. And the reason is, as things get hot, what happens? What typically happens is things get hot. They expand. What else happens? They tend to get weaker, right? As things get hot, they get weaker. Which you'd say, well, but that's good because I want the chips to be generated by the workpiece. But what else is happening? As this is getting hot, what do you suppose is also getting hot? The tool, right? So that's getting weaker as well. And you wind up with things, and as things get hot enough, you wind up with things like built-up edge. So instead of this material fracturing, like it's shown there, really nice little stack of chips up there, you wind up with, right at that interface, you wind up with the material melting and getting stuck, sort of welding itself to the tip of the tool. And when that happens, now you've really changed your whole geometry of your cutting. That tool's getting weaker because I just welded something to it, and it typically breaks the edge of the tool off. Okay, so that's not good. So tool wear, again, is something else you look at. As the tool wears, what happens to my dimensional characteristics of the workpiece as my tool wears down. It gets bigger, right? As the tool wears, think about it, if I've got a drill, as that drill gets smaller, my hole gets smaller. The same thing with a cutting tool like this. As that tip of the tool wears down, my diameter, if that's the diameter I'm doing on a lathe or a milling machine, whatever it is, that dimension's going to change. So tool wear is something I need to manage. The other thing that happens as tools wear, typically they wear by the certainly the edge, right, the corner or tip of the tool here, what's called, right at that interface. As that tool wears, I go from a sharp corner, as shown here, to a radius. What happens when I get a radius there? What happens as I start to get a radius instead of a sharp corner? Well, it's harder to create that shear angle, right? If I have a big radius there, my pressure effectively, or force on that tool increases, and that's not a good thing. I can get deflection of the workpiece, I can get all kinds of nasty things happening. So that's something you need to try to avoid at all costs. And again, just a little bit more on the chip formation, about the shear angles. Here's some photomicrographs of chips being formed. Sort of gives you a clue as to what's happening. And again, there is very much a science behind this. It just gives you some examples here of a tool, the chip, again, the interface of the tool and the workpiece creating that shear zone. Again, sort of stack up of chips here. The other thing that can be done to the tool is, instead of it being shown as it is there, I can put a little chip breaker on it. So instead of my tool, I'm going to try to draw this. How am I going to do this? Let me just draw the tool here. Hold on. Whoops. Instead of my, let me just do it here. Instead of that tool being drawn like that, or being made like that, you might make it like this. You have a little land there. Might make it like this. That's a horrible drawing. Let me try that again. Okay, instead of it looking like that, I'll get there eventually. So instead of it looking like that, might make it like that. What do you suppose that's for? What do you suppose that little groove, if you will, going through the tool is for? Why do you suppose I would do that? What am I trying to do? I'm trying to break the chips, right? I don't want a continuous chip. Yeah, what it does, it forces the material to go up into that little groove, and it just creates a you're basically making the chip sort of deform more, is what it is, and that increased deformation causes it to break. So that's called a chip break. You put a little groove in the tool, and the material, as it's being cut, just like you see here, is following the face of the tool. So if I put a little groove in there, maybe I can just draw it right on the tool. Might make it a little bit more. If I just draw it right on the face of the tool, so I make it look like that, right? I've got a little groove there. Oh my gosh. There we go. I can't get to my so I cut a little groove basically in the tool, sort of like that. And what's going to happen is that material is going to get pushed into that groove, and as it rolls back around, it's going to have an increased amount of deformation. Rather than just a straight shear plane, it's going to be forced into that groove and come up. And it'll cause the chip to break. So that's a way to control chips, to force deformation that will help us create separate chips, not one big string. And as we go into lab, we can spend some time on that. And here I just wasted my time trying to draw something I already have. Here's some good examples of that, right? couple ways you can do that. So you put that radius in there. In the first one here you've got a little bit of a land on the tool, and that's just to get some additional strength. Okay, if you look at these three examples here, the positive rake, I've got a dead sharp corner. Here I've got a little bit of a land there. Again, that's just for strength. That's all that's for. And another way to do it, besides cutting a radius in the tool, and this is a really good sort of image, it shows you what's happening. You put a chip breaker on the tool, and this is sort of not done as much today as actually getting it into the insert, because typically today you're using more insertable tools, and we'll talk about that in lab. But you're not using discrete tools that you can easily clamp a chip breaker on. But this is another way to do it, and that gives you a really good example of what you're trying to do. If you think about taking a piece of metal and you deform it as shown here versus here, in that second case, you've got way more deformation, meaning you've got an increased force on the material, and it's more likely to break. Right? It's easier to get to the ultimate strength, which is what I'm really trying to get to. Okay, and this is the bird nest example here. So this is a lathe operation. This is a continuous chip. You can see that just balling up. If you're machining stainless steel or something, it's really creates a sharp edge that can be very nasty. And this tends to get wrapped around the workpiece. Eventually, it breaks loose and comes flying off. It's not a good thing. Versus a discontinuous chip, like you see on the right here, being generated. And this is a good example of an insertable tool. If you look at this little parallelogram type shape here, this portion right here is a very common, it's an 80-degree diamond tool. The angles are 80 degrees, which is why it's called an 80-degree diamond, on the cutting edges. It's got a hole in it, which has a sort of an offset kind of pin that's on an eccentric. I can lock that insert in with a little wrench, and you turn that eccentric and it locks the insert in, pulls it back into the pocket. This portion of it here is the tool holder. Okay, the portion that holds it, that's not that's not a replaceable thing. I mean, sometimes they get damaged, but the insert is. The insert typically you'd replace after it gets worn to a certain point. And then there's another sort of toe clamp sitting on it here too, which holds that into the tool holder. And these inserts, these particular inserts have 4 edges per insert. So you've got the top, flip it, and then spin it 180 degrees to use. And when we get into the lathe work, you'll get an opportunity to utilize those. Okay, just some more examples of continuous and discontinuous chips, again showing the chip holder, chip breaker here. And again, just a little bit more on the angles that you create. All the tool angles are very critical. We're not going to get, again, too much in depth, but. And here's an example, a couple examples of some common lathe tools. This is just a piece of high-speed steel that those angles have been ground onto. And the various angles you look at, the side rake, the edge cutting, the relief angle, and the different axes of the tool. And again, on the right, what's shown here is an insertable tool, which today almost everything goes that way. Years ago, when I first started working in a machine shop, the one on the left here was what was being used, high-speed steel, and you'd have to grind that tool if you were running a lathe or whatever you were doing. You'd have to grind a chunk of high-speed steel, grind it into a tool, and that would be what you would have to do. And then as insertable tools became much more common, they took over basically. So you don't see much high-speed steel anymore. And why do you suppose that is? Why is an insert better? What drove a lot of that? What drove a lot of the insertable stuff? Think about CNC equipment, right? I want to have a repeatable situation. When my tool wears, I want to rather replace it with something that I don't have to adjust the machine or change my program or offset the tool, right? With the one on the left here, you had to. Every time you either made a new tool or ground an existing tool, as the tool wore, you would have to grind those edges to get it sharp again. If you're on a manual machine, it's not a big deal. If you're on a CNC machine, you got to reset all your offsets, and that can become, in some cases, change your program. That can be become a real issue. Where the insertable tool's on the right, you just pop the insert out, put a new one in. And it will repeat reasonably, because the inserts are dimensionally very consistent. Just to give you some idea, again, it's about friction, it's about cost, right? Those are the two factors that I focus on a little bit in manufacturing. And it really applies to machining, because as tools get dull or as materials are harder to deal with, friction becomes a big issue. And this is just the energy required to machine various materials. So as I'm looking to select a material, I want to pick one that requires the least amount of energy, right? Because I can have a smaller machine in some cases, but it's just easier to do. It requires less energy and typically less heat. So again, things like aluminum alloys, really down at the low end, very easy to machine, very machinable materials. Copper alloys being the same way, very easy to machine. I talked about high temperature alloys, typically high nickel alloys, Hastelloy, Inconel, things like that. Very hard to machine. You're looking at a 8, 9 order of magnitude difference between aluminum and some of the high temperature alloys. So they're very difficult to machine, require a lot of energy, and it's because they're high strength, right? You've got to exceed that ultimate strength, so therefore you need to impart enough energy to the workpiece to do that. And that's why these are harder. Steels are a very wide range. Some steels are, well, they're never quite as easy as copper or aluminum, but very wide range in terms of the alloying elements. And what else comes into play with steel? Why is steel such a wide range? Think about the states that steel can be in, right? Steel can be annealed, or steel can be hardened, right? Hardened steel, much harder to machine. Ultimate strength, much higher, and that's the whole thing that drives it. Titanium, same sort of thing. Different alloys have different properties to them. Stainless steel, same way. Okay, so that just gives you some clue as to what you're doing. If you've got again, something that requires a lot of energy to create a chip or to dislodge material, you're going to need higher horsepower machine, costs more. You need a more rigid machine, costs more. So that whole cost thing comes into play. And this is just a sort of again, really the point here is just to understand what's happening. That I'm creating temperature on my workpiece, which can be problematic, but probably more problematic is creating temperature on the tool. And what I'm showing here, and this is one of the things you look at, sometimes on tools you'll get a temperature failure, not right here, but right there. Why do you suppose you get temperature issues up higher on the tool? Think about friction for a second, right? If I've got a chip and that material doesn't break or doesn't curl, you've got a frictional force, high pressure, super high pressure on the chip, and it's being pushed across the face of the tool. You can get a high temperature failure of a tool, not right at the tip, but some a little bit up on the flank. So you got to think about the sort of the mechanics that's happening there. Okay, and this again is just some temperature stuff. This is a little bit beyond what we need to worry about too much here. But one thing I do want to mention is that what do we do with failures? Anytime you got a failure or something, if I design some kind of mechanism, I get a failure. What's the first thing I do? I take the failed part and I throw it in the garbage so nobody sees it, right? Right? Know what you do? No, that's not what you do. You look at it, you analyze it. Failures provide an infinite amount of information to you. And whether that's a fatigue failure, when you guys take machine elements, we talk a lot about fatigue and analyzing the failure, because it can tell you why it failed, and most importantly, how to prevent it from failing again when you replace it. What do I need to change? And tooling is exactly that way. If I have a tool and I get a premature failure where the tool broke or the tip got damaged or whatever, first thing you want to look at is the characteristics of that failure. And I'm not sure why you can see the images here, but it gives you some idea of the different kind of failures you can see. Thermal cracking, wear the flank, wear on the face is cratering. That's typically a temperature failure where it's back off of the cutting edge. It's back here somewhere. Because there's different things that you can do to change that. This has got some material sort of welded to it here. There's different things you can do to change that. Each one of these would potentially require a different approach to make it not happen again. Okay? If I'm getting wear like that, I might go for a harder material. If I'm getting a fracture failure, I might go for a little bit softer material. Okay, not in the tooling, not quite as hard and or brittle as what I've got. If I've got thermal cracking, do I have adequate coolant hitting the tool? Okay. I've got crater wear like this. Could be a coolant issue. Could be that I need to change the geometry of the tool so the chip's not in contact with that face for as long a period of time. Maybe I need to reduce my depth of cut a little bit. So there's all these variables that you got control of, right? And looking at the failed tool is a great way to determine, changes that I might want to make to fix that. And this BUE, I've never seen that acronym before, but it's built up edge is what it is. And that's where the workpiece material is actually welding itself to the face of the tool. Okay, so I would, again, probably a coolant issue. In that case, could be other things too, but most likely a coolant issue. Or you're just going too fast. Okay. Speed typically creates more friction, or more heat because of the friction of the workpiece against the tool. So that's something you might need to reduce. Okay, so and that is in everything you do in engineering, mechanical wise at least, you really want to analyze your failures. Okay, because there's a wealth of information there. You don't want to just say, I failed, I'm just going to replace it. Okay. And there's some equations out there that can be somewhat useful, but most times it becomes more of an empirical thing. But there's some equations out there that can be used to generate tool life expectancy. Gives you an approximation of it. But again, empirical data is going to be probably a little bit more useful. And that's that equation there. The things that you do spend a lot of time, so again, this is just some guidelines as to, depending on workpiece hardness, microstructure of the material, and tool life and the impacts they have. Typically, as things get harder, tools wear quicker. Cutting speed, typically cutting speed goes up, tools wear quicker. And again, you've got high temperature that's being generated. Another approach is to possibly change the material you're using to make your tool out of, or purchasing. Carbide ceramics are very common. You also see diamond tools, but very expensive, so not used as much as carbide and ceramic. This chart's sort of useful. It gives you an idea where these things fall. So in terms of cutting speed, in terms of tool life, right? So where do I want to be? I want to be over here somewhere, right? I want to go as fast as I can, right? Because the faster my cutting speed, the faster I can machine something. That's a good thing, right? And I want my tool life to be at its maximum. So if I could pick my spot in this curve, it would be up in the upper right-hand corner. Okay, but that's not life, right? So you want to get the best mix you can of tool life and cutting speed. And again, just a little bit more on tool wear and some of the failure mechanisms that you'll see. Thermal issues has a lot to do with tooling, and that's a big thing. So this is sort of tied in with what we talked about up above, same kind of thing. This is an interesting one too. I talked about tools. Maybe I started off with a tool that was dead sharp, right? As it wears, I end up with a radius on that tool. And what did that do to my sort of force profile? If you do a little like free body diagram on the interface of that tool to the workpiece, as that radius gets bigger and bigger, what's happening? I'm getting more and more force trying to push the tool this way, right? Because before I had a dead sharp corner, okay? I don't have a whole lot of force going that way. Most of it's getting imparted into the workpiece to create a shear surface. But as that radius increases, that tool, and I'm sure you can attest to this, when you're running a lathe, as that tool gets dull, right? The workpiece will want to actually move away from the tool. Sometimes it'll deflect away from the tool and you start getting a larger diameter than what you wanted. And your tool starts to get pushed away. If your machine's not very rigid, it'll actually push the tool away so you don't get a dimensional surface that you're looking for. Okay, so as the tool wears, or if you select a tool with a large nose radius on it, that's called the nose radius of the tool, you get the same effect. Well, why do you want to have a radius on there? Think about it for a second. Why don't I always just want to have a dead sharp tool? What happens to a dead sharp tool? Chips. How long is it dead sharp? Not very long, right. So you need to have some sort of a radius on there, and that's a mix, and that's something you need to, another thing you need to sort of design into your tooling. But the inserts that I talked about, you can get a radius of a 64th of an inch, you can get a radius, and that's about the smallest you get, up to maybe an 1/8 of an inch. So that's a huge difference, and depending on how rigid your machining operation is, in other words, how much it's going to deflect, and the material you're using, and a bunch of other factors, you need to pick that nose radius. The other thing that comes into play is think about what you're doing when you're machining, especially on a lathe, right? If I've got a feed rate, it's got a relationship to that nose radius. If my feed rate, in other words, how much I move the tool for every revolution, is greater than my nose radius, what do I wind up with? A nice spiral groove right down the part, right? So as that relationship gets bigger, feed to nose radius, those spiral grooves get bigger, right? So I can help myself either by reducing my feed rate or by increasing my nose radius on the tool. And typically some mix of those that you do. So if you've got, they're sort of competing things in that the smaller the nose radius, typically the better cutting condition I have. The larger the nose radius, the more pressure I'm generating, but I can go faster. So they sort of compete with each other. We'll actually do that in the lathe. Get to see that. Okay, and this is just, again, talking about tools, and some of the characteristics that we look at are things like hot hardness. In other words, as materials get hot, they tend to get softer, right? They tend to get weaker. Well, some materials are better in a hot state than others. Diamond being the best, high-speed steel being the worst. Toughness in terms of impact strength, in terms of wear capabilities, and those are sort of related to each other. And again, high-speed steel being the most forgiving, diamond being the worst, so it's the most broke. Wear resistance, again, diamond being the best, high-speed steel being the worst. Chipping resistance, again, this is directly tied into the toughness and impact strength. Again, the high-speed steel being the best. Cutting speed ability, diamond being the best, high-speed steel being the worst. And then thermal shock. And then finally, cost. Diamond tools are very, very expensive. So you're not typically going to use those unless you absolutely need to. And then depth of cut, typically they're all sort of the same except for diamond, which typically is very light, so it'll only be used for, again, where you need to and in a finishing operation. Many times you'll have a roughing tool and then a finishing tool. You might have a carbide or coated carbide roughing tool and finish with either a second carbide tool or maybe a ceramic or even a diamond if you need to. Okay, and then these are just how they're made. The tools are made. Tools are coated many times. Carbides especially, they'll be coated with a harder material like an aluminum oxide of some sort just to get increased wear resistance. Again, this just gives you a little bit more of the characteristics of the tool, sort of a summary of that table. They sort of say the same thing. And here's just some examples of some cutting, insertable cutting tools. And you can see, we talked about chip breakers, right? You can see that they're actually generated in the insert as part of the insert process. You can see some of these here. They all have a little bit of a chip breaker to them, so that chip will curl and then break. And these are far and away the most popular used, today. The high-speed steel and that stuff isn't done. Either ceramic or carbide. Far and away the most common. But all different shapes. We're only showing a couple here. The 80-degree diamond, that's probably a 55-degree diamond. I think that might be a 35-degree diamond. And that's the angle that is at the edge of the cutting tool. But there's lots of others. There's other kind of threading tools, grooving tools, and we'll go through that more in lab. And this just gives you some examples, and it's sort of common. It's sort of intuitive, I should say, that the closer you get to a circle, round tool, the increased strength you've got, and the ability to chipping and breaking of the tool, the more you get to a sharp corner, the worse that gets, right? So you can see that the 80-degree diamond is sort of in the middle, which is why it's probably the most common. The other thing is I can use this. So there's two kinds of cutting, broadly speaking, that you do on a lathe. And maybe I have an example of this before I draw it. So if we look at these two, if we look at this one, if we look back at this picture where we're talking about discontinuous chips, this is called a facing operation, meaning that's the face of the workpiece, and my tool's moving from a diameter towards the center of the tool to create a nice face, okay? Contrast that with this kind of operation here, where I'm actually turning the diameter, okay? Well, if I've got an 80-degree diamond tool, I can do both with the same tool, right? Because I've got an 80-degree diamond, I've got a 10-degree, or a 5-degree rather, relief angle between the face of the tool and either cutting edge. So I can face with it, or I can turn with it. And you can sort of see that in this picture. As that tool's moving across, you can see I've got a 5-degree angle. You can sort of see, you can see it better on the screen. A 5-degree angle between the tool and the face of the part. If I'm turning, same way. I've got a 5-degree angle, so I can use that same tool to face and to cut and to turn, which is why it's another reason why it's so popular as a lathe tool. Because I don't have to change tools. If I don't have to change tools, I don't have the time required to change that tool, and I'm only using one tool. Okay, so that's a big advantage with that style of tool. All right. So again, those are insertable tools. Talking about edge strength. It's pretty intuitive when you look at it in terms of the sharper that tool gets. It may cut better, but you're losing some strength typically too. And again, this is just talking about the various tooling materials and sort of the evolution of tool materials and how the machining time has dropped with that. If you look at the slope of this, as we've gotten better tools, we can go faster. Right? That's what it comes down to. So, back in the 70s and 80s, that's when a lot of the coated carbides first came into play. And again, just another chart here that shows you sort of the overlap, strength and toughness, hot hardness, and wear resistance. Right? Typically can't get both. As shown here, the ideal cutting tool would again be up in the upper right-hand corner, but you can't get there. So typically they tend to some extent at least, conflict with each other. Okay, so we've talked about heat. Heat's not our friend, right? We talked about cutting fluids. In all these examples here, you're probably more concerned with cooling capabilities than lubrication capabilities. Okay. But all we're really showing here, and this is pretty intuitive as well. You know, and this is a great example. If I'm drilling here, right? Do I want to be spraying my coolant back here? No, right? Of course not. You want to have it on the tool. But you see that. You know, that's just bad setup practice, where people aren't really paying attention and they take the coolant nozzle and instead of setting it up where it's going to blow right on the interface of the tool and the workpiece, it doesn't. So again, same sort of thing you're seeing here. Doesn't do much good to spray the coolant back there. It's obvious, but it's not. How's that? So the best thing to do is have a coolant nozzle. What you're seeing here is the coolant is actually fed through the tool, right? And blows right out on the insert, right at the interface of the tip of the tool and the workpiece. That's the best condition to have. Okay. We'll talk about this a little bit more in lab. These are some relationships that you sort of need to get your head around a little bit. RPM versus surface feet per minute. Okay, RPM is how fast the tool or the workpiece is spinning. Surface feet per minute is basically taking the circumference. Because really what you're interested in, if you think about it, am I interested in RPM or am I interested in surface feet? So surface feet is how fast the material is going past the tool, right? So I'm interested in surface feet. And what happens is my diameter changes. Think about that facing operation. Imagine I've got a piece of bar stock this big, right? And I start to face across it. What happens to my surface feet for a constant RPM? When I'm in a big diameter, it's much larger, right? Because it's the circumference, really, is what I'm thinking, is what you're looking at, is the circumference of the workpiece and that relationship with the RPM. So as I start on a piece of material and I face it, ideally what I want to do is increase the RPM as I get closer to the center. So I keep the surface feet constant, right? You can't do that on a manual lathe, but you can on a CNC lathe. So that's sort of the relationship between RPM and surface feet. That's actually what I'm most concerned with, is surface feet. And then inches per revolution. Inches per minute is what I'm trying to drive. I want to go faster, right? Inches per revolution is, again, for every diameter, every rotation of the workpiece or the tool. Depth of cut, talked about surface feet. Average surface feet, again, would be if I've got a constant RPM. And then finally, what we'll get to with related to milling tools is inches per tooth per revolution, okay? Which is how you would specify a feed rate. In inches per tooth, meaning if I've got 6 cutters, say I have a 6-flute end mill, or a 4-flute end mill, keep it easy, a 4-flute end mill and a 2-flute end mill, right? What I'm really interested in is the amount of material that I'm removing with each tooth per revolution, okay? And we'll talk about that in lab, get more into that. It's easier if you've got a tool in front of you, you can really visualize it, so we'll talk about that. Okay, so that's a brief sort of overview of machining. I think I have another, yeah, this was what we did in lab. And do I have another one on machining? Let me see. Yeah, I think that's a repeat. Yeah, so we got one more, I think, on machining, talking about some other operations, milling, broaching, gear cutting, which are sort of specialized a little bit processes. We'll pick up on that in lab as well next Tuesday.